Welcome to Algorithms class. You will have these lectures also recorded and posted on Moodle and on YouTube, so you can choose where you want to watch them. There are more than 700 students enrolled in this class, right? So if each of you send me an email once in 10 days, that will be pretty much a disaster, right? So we have a sacrificial lamb, course admin, Amin Malikpour, and here is his email. So always first try to resolve your issues with him. And if this doesn't work, then email me, or even better, stop by my office. You can see on the course webpage when my office hours are. My office is at CSE on the 5th floor outside of the locked area. So when you exit the elevator, just turn right and go all the way down the corridor. So we will have a couple of homework problem sets. And if you are new to algorithms and you find initially the problems too hard, you are welcome to consult with your colleagues. But you have to write down your solutions in your own words. So no cut and paste, otherwise our submission system will detect that you are plagiarizing, right? So you have to write down everything in your own words, but you can ask also me for help with the problems if you come to my office hours. So initially, students find this course quite challenging, but as we progress, you get to practice problem solving and things get easier if you are studying regularly. We will be covering quite a lot of material, so please make sure you don't fall behind because it's really hard to catch up. And your grade will be based 20% on your homework, so a relatively small portion, 40% on the midterm, and 40% on the final. And midterm usually covers the first half of the material, and the final covers only the second half of the material. So make sure you do well on the midterm because you will not have a second chance for the first half of the material. Okay. And on both the midterm and the final, you will get brand new problems that you haven't seen before, but if you follow the course closely, you will pick up all the tools and all ideas necessary to solve all the problems, right? So I guess that's about it for an informal introduction. So what is this course about? It's about designing algorithms for solving problems using a computer, right? An algorithm is something that we eventually implement as a code in your favorite language. But before you implement something, it's a very good idea first to make sure to convince yourself that the solution, independent of its implementation, is sound and reasonably efficient, right? So we will give you kind of exemplary implementations of some of the algorithms that we will cover, but we will concentrate on problem solving. So in your exams, you will either describe your algorithms in plain English, or you can write a pseudocode of the kind that we are going to use in the lectures. Why do we do it that way? Well, you get quite a few courses in which you practice programming, but unfortunately, you don't get enough courses in which you practice problem solving. And you will see on the course web page, there is a sheet with Microsoft interview questions. And all of them are essentially kind of tricky algorithms. Because, you know, if you get a job after a year, even lousy programmers like myself eventually learn how to program. But getting good problem-solving skills requires much more time and practice, right? So if you are in doubt, and you know, students sometimes ask me, why do I have to learn to design algorithms? If I need an algorithm, I Google it, and lo and behold, I can find it on Google. But unfortunately, this is not true, because the kind of problems that we solve today are very different and use very different tools than kind of problems that we solved when I was your age, which was sometimes in AD, but you see, computer science is very rapidly changing field. So rather than learning, I will never ask you to memorize particular algorithms, because unless they're totally trivial, like merge sort, right? Because you can, in fact, basic algorithms, you can always look them up in a reference manual or in a textbook. So what we are going to focus is to learn technique that can be used to solve new unfamiliar problems that arise in computer science today, right? So during the course, we will survey design techniques like divide and conquer and greedy and dynamic programming and max flow and various types of string matching and so forth. And particular algorithms will be mostly used just to illustrate the technique. So we want to focus on the techniques to enable you to solve new problems that you might get at your workplace once you graduate. So, and the emphasis will be on developing your design skills. Okay, so textbooks. You have two choices. If you are just looking for a good textbook, then this one is probably by far the best one. So Kleinberg and Tardosh, Algorithm Design, and you can get it for a small fortune at UNSW bookstore. Some students tell me there are other ways to get it, but I won't go into that. Good aspect of this is that it's very readable, and unlike most of computer science textbooks, it's actually extremely pleasant to read, right? So it's an excellent textbook. By drawback is if you give a fortune to buy it, you won't be able to use it later as a very good reference manual, because it's really written to introduce you to algorithms in a most gentle way, right? Now, if you want to make a better use of your money, you can also get the alternative textbook, which is Corman, Laserson, Rivest, and Stein, which is kind of considered to be the Bible of algorithms, Introduction to Algorithms, preferably the 3rd edition, and it should be also available at the bookstore. And good feature of it is that it can be used later as a reference manual, because it contains really a vast number of algorithms, and even if you need something not there, in all likelihood, the reference will tell you where to look. So in this sense, it's an excellent reference manual But unfortunately, it's quite formalistic and written in a rather dry style that puts you to sleep or increases your beer consumption. So I let you choose which one of the two you pick. We will not follow line by line either of the two, but everything that we do will be possible to find in these two textbooks and notes on these slides, right? Okay, so why should you study algorithms design? As I told you, just look at interview questions. And they are all algorithms questions. And it's not very modest, but I have to say I often get email from my former students when they get a job at Google thanking me for covering in this class precisely what they were asked on their interview. Okay, so by necessity, this course does involve kind of a fair bit of mathematics, right? Simply because we are no longer designing word processors and elementary things like that. And just like in any engineering, mathematics is used to design kind of more serious stuff. So what is the role of formal proofs? Well, actually not formal proofs, but informal but rigorous proofs. When do we need to prove that an algorithm we have just designed terminates and returns a solution to the problem at hand? You see, unlike the Corman, the second textbook, the boring one, right? That proves even totally obvious things for reasons that I really fail to comprehend, just to kind of keep everything totally rigorous, we will be quite sloppy in the sense that we will not prove, say, the convergence of time bound of an algorithm if this is obvious from the description of the algorithm. But unfortunately, very often you cannot tell from the recipe, so to speak, from the pseudocode of an algorithm that in fact it produces the object that you want to compute. And it is in these cases when you need to prove that your solution is correct, right? And possibly to estimate its runtime, right? So we will cover in this course algorithms. In fact, soon we will see an example. Algorithms that you simply cannot tell from the description that they produce a correct solution. Okay? So in this case only, we will prove the correctness and possibly give a time estimate if it's non-trivial. Okay, so here is an example of something that theoretically you should prove that is correct and you should estimate its running time, but for this type of algorithm, this is essentially obvious. So let us see. How deep is the recursion? How do we do merge sort? You split your array into two, then you call merge sort on both halves. You get two sorted arrays, and then you merge them, right, by moving element by element into a new array, right? So how deep is the recursion? How many times can you split your array into two subarrays?
Ceiling of log base 2.
Ceiling of log base 2. Good that you said ceiling of log base 2, because I'm sure if there are here math students, they will hate me for that, but we are going to do engineering mathematics, which means if it sounds right, it must be right, okay? So ceiling log 2 will not exist. It will be called log 2. Why? Well, because the error by kind of rounding off in algorithms that we will do cannot change significantly the runtime. So you can split the array in half log n many times. At each step, from already sorted sub-arrays, you merge them together. How many steps does it take to merge two arrays together in terms of their size? Linear time, right? C times n many steps. So let's see if you total all these. On every level of recursion, you make O of n, a linear, some constant times n many steps. There are log n many layers of recursion. Thus, the algorithm runs in times C times n log n, right? By the way, on the course website, the very first document is a little booklet, actually partial booklet, because I never finished it, which I wrote many, many years ago when I was young and handsome, that will help you to review all the necessary things about logarithms and about asymptotic notation, big O's and big omegas. So please take a look there, and there are also interesting homework problems there. You might want to play with them. Students find them very interesting. Okay. So merge sort obviously terminates in O of n log n many steps. Notice what I was telling you is actually proved by induction, right? Because what we did, we assumed that in order to prove, for example, that merge sort is correct, we assumed that in the previous layer, the sub-arrays were correctly sorted. Merging them produces correctly assorted array. Thus, inductive step also holds, and consequently, you get that the algorithm, the whole algorithm is correct. But this is all quite obvious, and we will not waste time making proofs by induction if it's pretty trivial, okay? So, but as I said, quite often it will not be clear from the description of the algorithm that algorithm, for example, never enters an infinite loop, right? And fails to terminate. Or maybe it is not clear that it will run in exponentially many steps in terms of the length of the input. So if your input is an array of size n, you have to have a guarantee that it will run in polynomial time, and hopefully a low-degree polynomial, like linear or quadratic. Cubic, that becomes tricky even when n is of the order of thousands. And if it's 4th degree, that's kiss it goodbye, because you will get as bold as myself by the time your algorithm terminates. Okay. Now, but sometimes it's not clear from the description of an algorithm why, even if the algorithm terminates, why it produces the desired solution, as you will soon see in an example. So proofs are needed only for such circumstances. So they are not academic embellishments. We don't do them because that's intellectually, proper way to do it. Simply, we will do them only when there is no other way to see that your algorithm works, right? And this will be indeed the case, and sometimes this will be quite a non-trivial result. For example, when we do max flow, you will see that. Okay, but for that reason, so that you don't get a wrong idea, we will never, as a matter of principle, we will never do silly things proving something that is obvious, right? We leave this to the mathematicians when they suffer insomnia. So let me give you an example of an algorithm that it is absolutely not clear that it does the job. And moreover, it is even not clear that that problem has a solution, right? So assume that you are running a dating agency and have n men and n women as customers. Now, why n men and n women? Because that's a very old example. Before, it was politically correct to put everything in LGBTQRSF circle, you know. So we will be old-fashioned like Tony Abbott and say we are running a dating agency and have n men and n women as customers. And they all attend a dinner party, and after the party, every man gives you a list with his ranking of all women present, right? So if there were 10 women present, he will first put one that he liked the most and so forth. And then also every woman will give you a list of men ranked according to how much she liked each of them. So now, your task is to produce a stable matching. So what is a stable matching? You have to, yes?
Sorry.
Yeah, feel free to stop me at any time. A good advantage of watching this on YouTube is that you can stop me and ask questions, right? So please don't be shy.
Did this problem come out of organ donations?
Oh my. Look, I faint when I see blood, and now you are talking about organ donations. Now I cannot continue this class. I mean, all what I see is livers and hearts floating around. No, but you are very close. Well, maybe they used it also for organ donations, but it originated in the United States. Like in every other country, once young doctors graduate, they have to go for residency, right? And so each doctor orders all the hospitals available according to his preferences. And so then doctors apply to the hospitals, then hospitals examine their CVs, and they write a list of candidates in decreasing order how much they like each of them. And the point was to pair doctors with hospitals in a stable manner. So what is a stable manner? So this means, for simplicity here, we will assume that we have equal number of items to match, n women and n men, right? So you want to make pairs of a man and a woman so that the following never happens. You have two pairs, and the man from the first pair prefers woman from the second pair to the one that he's matched with. And that woman also prefers that man to the man she is matched with. Why we want stable matching? Simply because there is nothing to prevent the man from the first pair to abandon the partner that he is matched with, and the woman from the second pair does the same, and they run away and mess up your matching scheme. So you want to prevent, okay, that it happens that this man prefers this woman to the woman he's matched with, and also this woman prefers the same man to the man that he's matched with. So it's a very natural requirement. So the question, okay, let's see examples. So you can see in the first, so the arrows here means the preference. So M1 prefers W1 to W2, and W1 also prefers M1 to M2. M2 also prefers W1, and W2 prefers M1. So here is a stable matching. Why is it stable? Well, this first couple we have no problem because W1 is the first preference of M1, and M1 is the first preference of W1. How about the second couple? Well, M2 would prefer W1, but W1 doesn't like him. She likes better M1, and so tough luck. M1 will be matched with W2. Similarly, for W2, W2 would prefer man M1, but again, he prefers W2, so the matching is stable. While this matching is unstable, right, because M1 prefers W1 to W2, and W1 prefers M1 to W2, so these two couples will break, and a new couple here will be formed, right? Now notice sometimes it can be trickier than that. There can be several stable matchings, right? For example, if you have this kind of circular matching, it's easy to see that both this matching and that matching, they're both stable, right? So sometimes there can be more than one stable matchings, but why should there always be at least one stable matching, right? And lo and behold, you can see this is non-trivial. It's not clear at all why a solution exists, let alone how to find it. And this is a beautiful problem because proving that there exists a solution is done by effectively constructing a solution. So proof of existence will be effective in this case, as it is called, because we will provide an explicit procedure for which we can prove that indeed it always eventually stops, it produces a matching, and moreover that this matching is stable. So let's see, and this is called Gale-Shapley algorithm. Let us see. Okay, let's first see why don't we brute force it. So how many pairings are there in total? N factorial, beautiful. Why n factorial? Well, you can line up all the men and keep them fixed, and then any placement of ladies, right? You can permute the ladies in any way you want, and lo and behold, it will produce a matching. But the trouble is, n factorial is huge. It's worse than exponential. 2 to the n would be exponential, and n factorial grows even faster. It grows as n over e, where e is the base of natural log, 2.71 and so forth, to the power n, right? Which is approximately equal 2 to the n log n, so it is worse than exponential. So in this case, there is not a slightest chance to brute force the solution. By the way, on the exams, you get partial credit for your work, except for proposing a brute force solution. Because why the heck would you take algorithms to come up with a brute force solution? So if you do brute force solution, you fail and you get sent to Siberia, okay? Extended vacation, winter vacation. Okay. So, can we find a stable matching in a reasonable amount of time? And remarkably, the answer is yes, and this is using the Gale-Shapley algorithm. So how does it work? It produces pairs in stages with possible revisions. So as we construct pairs, some of them might be destroyed further down the line. So revisions are allowed. So let's introduce the terminology. A man who has not been paired with a woman is called free. By analogy, if he was paired with a woman, he is called a slave. Okay? Don't tell my wife I said that. So how shall we work? Well, men will be proposing to women, and women will decide if they accept a proposal or not. So we start with all men free and happy. So then we do a while loop, okay? While there exists a free man who has not proposed to all women, we shall do the following. You pick any such man, and you have him propose to the highest ranking woman on his list that he hasn't already made a proposal. So every man can propose to every woman at most once, right? Because in each round he will be proposing to the highest ranking woman that he hasn't proposed yet. Now, if no one has proposed to that particular woman already, right, she always accepts the proposal, and a pair MW is formed, right? So he proposes to a woman. If she is not already in a pair, she always accepts. However, if she is already in a pair, then if the man who proposes ranks higher on her list than the man that she is already in a pair, she dumps this man, right? How unusual, never happens, and accepts the proposal of the higher ranking man. Right? Okay. Then the previous pair is deleted. A new, and then M prime becomes a free man, and a new pair is formed. Right? Else, if the man who proposes is lower on her list than the man that she is already paired with, she refuses the proposal, and the man M remains single, right? So you understand, for as long as there are free men around, right, you take one of them, look at his lists of all women, all right, ranked lists, pick the highest ranking one that he hasn't proposed yet. He makes the proposal. If that woman is free, she always accepts. If she is already in a pair, she accepts if the proposing man is higher on her list than the man she was already paired. So now, the claim is, so notice, often happens that a man who proposes is accepted, and now her previous partner becomes free. So you get one man less free, but now another man becomes also free. So it might happen that the number of free men didn't drop at all, because one accepted, the other was dumped. So the number, so it's not clear that you cannot keep cycling like this, men getting into couples and then being dropped and so forth. So it's not clear that this algorithm will eventually stop. But it will stop after at most n squared many rounds of the while loop. Why? Well, every man can propose to a woman only once, because he is always allowed to propose to the highest ranking woman that he hasn't already proposed. So every man can make at most n proposals. There are n men, so in total, at most n squared many proposals can be made. So the algorithm will eventually stop. Okay, so let's see now. Second claim, that the algorithm produces a matching. What is a matching? It produces a matching, meaning every man is paired to a woman. Why is this so? Well, assume that while loop has terminated, but there is a man that is still free, right? Well, but he has proposed to all of the women on his list, right? Because the while loop exited. Because a woman always accepts when she is free, it means all of these women are already in a pair. But n women in a pair means also n men in pairs. So it's impossible to have a man who is still free. So after the while loop has exited, you must have a matching, right? Now the main part is to show that the matching produced in this way is stable, right? And notice we are using here kind of our favorite method of proving things, namely by reducing the contrary assumption to an absurd, right? By proof by contradiction. So let's see. So notice that a woman is always paired with men of increasing ranks on her list, and a man is paired with women of decreasing ranks on all lists, on his list, and lo and behold, this is how it happens in life, okay? So assume that the matching is not stable. So you have two pairs, and you assume that M prefers W prime, and W prime also prefers M to M prime, right? Since M prefers W prime over W, he must have already proposed to her, because he always proposes in the decreasing order of how much he likes them. If he likes W prime better than W, it means he has already proposed to her. And two things could happen. She rejected him, but this would mean that she is already in a pair with someone she likes better. But that's impossible, because here we claim that W prime prefers M to the person who she is with. right? So, or she did accept the proposal from M, but after a few rounds, she dumped him for someone she likes better. But this is, again, contradiction with the assumption that she likes M better than M prime. So, and this is a contradiction. So, lo and behold, the matching thus produced is stable. So you see this beautiful little algorithm shows you that sometimes it is non-trivial to see that algorithm terminates. It's not obvious after how many steps it terminates if it does. And finally, it's not obvious that it produces the solution that you need. Only in such circumstances will we prove by some not formal but rigorous argument that the solution is correct. And often this won't be totally easy at all. Okay. So this is, okay, so in these slides that come now, I have a few puzzles. And why puzzles? Puzzles are good for practicing problem solving because they often use exactly the same design techniques as serious algorithms, but do not involve nitty-gritty details that algorithms often have by necessity of their setup. So I encourage you to go, and there are more puzzles on the website. And if you have good puzzles, please email them to me. Because it really helps your algorithm design skills, and it's fun. And I have to tell you, because I know that there are quite a few computer science students that have math anxiety. Usually people have math anxiety because they were taught math by monsters. I'm serious. Often math is taught as an intelligence test. And people get intimidated and they shut down and stop thinking about the problem and get an idea that they are not capable of understanding math. And you will think I'm nuts, which I might be, but anyhow, problem solving comes natural to humans if they don't feel intimidated and put on a test, on an IQ test. So if you are new to problem solving, it might be challenging in the beginning. But doing math exercises has exactly the same effect on your brain as going to the gym, like myself, that increases the volume of your muscles. Okay? So practice makes you genuinely better, and everyone can improve his problem-solving skills. I don't know how many of you play chess, but if you play against someone who studied chess, like openings, middle game, and endings, you have absolutely no chance of winning him, even if you are much smarter than he is. So the same applies to problem solving. More you practice, easier it becomes. Okay? So just hang in, and in the beginning, you might ask your colleagues for advice, or you might ask me, right? But it's important, you see, even if you get a homework problem that you cannot solve, please, by all means, try to solve it. You see, because when you see a problem and you immediately see its solution, it's of zero use. If you try to solve it and you fail, then you can realize what step was non-trivial and what actually the solution does. Otherwise, it just flies by you. So please do an honest effort because it's very much worth it. You see, nowadays, a lot of computer science jobs are outsourced to India or China or Vietnam. What companies don't like to outsource is their algorithms, right? They keep these as a secret in the house. Okay, so look at these puzzles. They are kind of examples of divide and conquer or examples of lower bounds to prove that there is no algorithm of certain kind. Or you have just kind of logic puzzles like this. And if you find it hard, next slide gives you a hint to paint this grid in this way, and then the solution is much easier. Similarly here, the question is, can you cover a board like this with dominoes like that? Because, so how many? You have 62 cells. So with 31 dominoes, you might be able to cover it. What do you think? Is it possible to cover it? No. Why?
Because you asked, that means that it's not.
That's true. Here it is. If you paint the board, why is it now obvious that you cannot cover the board with dominoes? Every domino covers how many white and how many black cells?
Uneven amount of white and
Exactly. You see, this board has fewer black cells than white cells, but every domino covers exactly one black and one white cell. So no way that you can cover the board with dominoes. Okay, and here is something about cities in some strange place they call Elbonia. And so this is for your entertainment. And now we have to do serious things, right? How do we add two numbers? How do we add two numbers? What's the algorithm to add two numbers, say, in binary? Well, this is how we do it, bit by bit. And each operation involves adding 3 bits together, which can be done in constant time. So the conclusion is that the result is obtained in linear time. What does it mean, linear time? In number of steps that is proportional to the length of the input. Okay? Now, is it possible to add in fewer steps than linear time? Can you add two numbers, two n-bit numbers in fewer than c times n many steps?
If you got the right architecture, I'm guessing you can.
you can, if you store the sum of these two numbers just from 0 to 9, you store different combinations of them.
Okay, so let's see. In order to sum two numbers, you have to inspect every bit of them. But there are n bits. So if you cannot inspect several bits at the same time, then this is not, yes?
Could you not inspect like a large set of bits all at once using the right architecture?
Okay, so here in this course, we will do only sequential algorithms. In the advanced version, in the advanced algorithms, it's actually called advanced and parallel algorithms. We were supposed to also look at parallel algorithms, but I never actually do it for one reason. All the truly useful parallel algorithms are trivially parallel, which means they all, you know, if you have to run independent cases from 1 to 100, you send them to 100 processors. But this is not genuinely parallel way. Truly parallel methods involve lots of information exchange. So this is usually formulated as the principle that most parallel algorithms are trivially parallel, so we don't kind of study them. But you are right. we will here assume that the algorithms are sequential and that, okay, so you see x's do not have to be bits. They can be bytes, right? So, but again, the principle is the same. Then every byte has to be inspected at least once. So the conclusion is that there is no faster way to add than linear. Okay, so how do we multiply two numbers? Well, this is how you do it by the method you learned in high school, right? How many steps elementary steps does it take? Well, you can see it takes about n squared many steps, some of them multiplying byte by byte or bit by bit, depending on your architecture, and then you have to do a whole bunch of additions. So this algorithm runs in quadratic time. The question is, can you multiply two numbers in linear time? Anyone knows the answer? Well, let me help you. No one knows the answer. It's still an open question. We cannot prove. People suspect that multiplication genuinely takes n squared many steps. Well, that it does not take, that's wrong what I said, that the multiplication takes more than linear many steps. But no one has been able to prove this rigorously, that in fact, no matter how clever your algorithm, you cannot multiply in linear many steps. But the question is now, can you do it faster than n squared many steps? Sorry?
N log n.
Say n log n, right? Now, there is a story about that. One of the greatest mathematicians of 20th century, Andrei Kolmogorov, conjectured that you cannot do it faster than n squared time. And lo and behold, he started a seminar on complexity theory at Moscow State University. And on the first meeting, he conjectured that you cannot do it faster than n squared. At the second meeting of the seminar, a 23-year-old Russian Karatsuba came with a proof that you can do it faster than n squared. You can do it in about time n to the 1.67 something. And Kolmogorov was so shocked that he wrote the proof and published it under Karatsuba's name and canceled the seminar, right? So that's a little bit of history. In good old times when we didn't have iPhones, but we were solving math problems. So let's see how this young fellow Karatsuba, how he did it. Idea is to use divide and conquer. But in order to understand the clever trick, first we will try to do it simple way, and of course we will fail, but we will figure out why we fail and then introduce a fix that Karatsuba came up with. Okay. For those of you that have weak bladders, do you want a 5-minute break or shall we just continue? How many want a break? Okay, 5-minute break for everyone. Hi.
I'm back again at Disney.
Good,
It was
good.
like doing ACM last year. So basically, I have my previous coursework, like for the entry-level algorithms course. I was thinking about like, well, I actually tried to enroll in 980 on the website by myself. However, it's not really doable, so I guess it probably...
Okay, you have to go to the student office and they have to create extra space, but you tell them that I approved your enrollment and they will help you.
Like, do I need to write you an email and I'm full of what to become?
Yeah, they might ask you for that. So just drop me an email, I'll reply, and then you go talk to them. Hey.
When you're, if you can, like when you're answering questions or like people are saying things from the crowd, it's hard. They don't pick up on the mic. If you could, like repeat.
Yes, repeat the question. Very good. Thanks. Yes.
Probably about a year ago now, I was watching this pop culture documentary on algorithms, and they talked about the matching one, which is, my understanding was that they developed the algorithm in matching donors to waiting lists.
Yeah,
It
interesting.
was a problem in the UK hospital, NHS hospital system.
Huh.
I'll send you the documentary.
Ah, thanks. I read somewhere that it was for residency in the US, but you might be right. Maybe I'm getting a bit.
No. It was one of those documentaries where it's like for people that come home from work and eating dinner and just want to watch something in front of the TV rather than rigorous. But I'll send it to you.
Sounds good.
Yeah, they touch on others and how it's a pop culture exploration of how our lives are enriched by algorithms.
Very good. I'll be very happy to see that. Thanks.
What's the difference between 3121 and 3821?
Sorry, say it again.
What's the difference between?
Okay, I'll explain that when we
just
start.
hard in the exam or there's more things to try?
I'll explain that.
I was just wondering that for this course, is it a better way to just to do the problem solving, just like writing the pseudocode first, and then to just like using the computer science technology, just like programming language to represent it and to value if your method.
Yeah, absolutely.
Right.
That's a very good point. I'll mention this when I start. Thank you.
Will you be talking about the difference between extended and non-extended?
I'll explain this now.
Have you heard the puzzle about the person that, based on eye color, like there are lots of people stranded on an island, and based on eye color, after a certain number of days, they all work out what eye color they are?
No, send it to me.
Yeah.
I might have seen something similar, but maybe not.
I was just wondering when you would normally hold the midterm.
It's 6th or 7th week.
Okay.
Sometimes
What's the
6, sometimes
breaks
7.
between 5 and 6. So 6.
Yeah, so most likely 6
Okay.
or 7.
Is there going to be a way, if I'm not here week 6, for me to catch up on that?
I'll give you makeup midterm.
When do you normally decide? What time do you normally decide on when you take
When I can estimate when I'm finishing the first part.
If it's 6, I'm up.
Okay, let us start. Okay. So, oh yes, so I was asked a few questions. Let's see if I can remember them yet still. First, what's the difference between 3101 versus 3801 and 9101 and 9801? The extended stream involves a little bit, well, it involves more material, right? What we don't have time to do in this course is randomized algorithms, and they are becoming increasingly important. So I would urge you, even if you are not enrolled in the advanced part, you might find it really useful to at least watch the recordings. Yes?
For those thinking about it, can they move from the non-extended?
I believe you can. I believe you can. I don't know how this works now because they changed the kind of student office setup, but if you go and pester student office, probably I'll send them email that's okay. That's one question. Oh, and on the exams, you will have probably a homework or two more than the regular stream, and you will have a problem or two on the extra problem or two, or on the midterm and on the final. And during the midterm, it will be, so the midterm is always during the class time. So also the midterm, extra midterm for the extended class will be during the regular extended class. That was the first question. What was the second question? Sorry, I'm getting seriously senile. Can someone remind me? There was another question. What was the second question? Not 3821, but yes?
Using your program technique.
Okay. So, unfortunately, just due to lack of manpower to do the logistics, I cannot give you programming assignments simply because we don't have enough manpower to take care of that. But I will give you, for some of the algorithms, kind of sort of nice, clean implementation of the algorithm. But I urge you, so we want to maximally concentrate on problem solving, right? But I urge you, after you write the pseudocode, to hack it quickly in your favorite programming language, because when you program something, you are forced to think about every single detail. So you don't really fully understand an algorithm until you implement it and test it. So don't be lazy, even if it's not for a grade. Please try to implement. And the implementations are always straightforward. There is nothing really terribly messy in this course because we are doing programming techniques, right? Design techniques. Okay, so let's go back to trying to speed up multiplication to make it run in less than n squared O of n squared many steps. Well, divide and conquer works by splitting the problem at hand into smaller subproblems. So let us take, if we have an n-digit number, let's split it in half. So then we have a more significant part that has n over 2 many bits, and less significant part with also n over 2 bits. So then you can see how A is represented in terms of these parts. A1, you have to shift it for n over 2 many bits, and then you just add A0, the less significant part. Similarly with b. Now, if you multiply a and b together, you see that this reduces to multiplying these numbers that have only half as many bits as the original number. So presumably, they can be multiplied faster. So what are we doing here? Here is the pseudocode of the algorithm. You split, you take more significant part, store it as A1, less significant part as A0, the same for B. Then you multiply A0, B0, A0, B1, A1, B0, and A1, B1. And then because of this formula, right, the A1, B1 has to be shifted for n bits, and this sum for n over 2 bits. And behold, this is what this does. W is A1, B1, and it's shifted for n bits. This is shifted for n over 2 bits, and then you just add x. So how fast is this algorithm? Well, we don't have an explicit formula for that, but we can easily form a recurrence. You see, let's call T of n the number of steps needed to multiply two n-bit numbers, right? Then the work needed to do that, so T of n, has been reduced to 4 times 4 multiplications of numbers that are half the size. So it's 4 times the time needed for half-size numbers. And plus you have a linear overhead because you have to do this, this shifting, right, and adding. So this takes linear time. So this is your formula. And now we have to estimate the growth rate of the solution T of n if we know that it satisfies such recurrence. Now, some recurrences can be explicitly solved for, as it's the case here, but we will try never to solve explicitly recurrence because we are not interested in the exact solution. We are interested only in the asymptotic growth rate. Is it quadratic in n, is it n log n, or is it linear, right? So one can show that if T of n satisfies this recurrence, then the solution is precisely that. N squared c plus 1 minus c of n. How do we prove this? We prove it by fast induction, induction on number of bits, right? So we will assume that this formula is true for numbers with n over 2 many bits, and we will show that this implies that the solution this holds also for n many bits. Well, for n many bits, we have this recurrence. Now we know T of n over 2, given by this formula. You substitute it here, and after a bit of algebraic mumbo-jumbo, you get that also T of n satisfies this solution. So what do you think? What's the problem with such an approach? This is called guessing and then proving.
I don't know how to guess.
Exactly. How would you guess? Look at the guess. I mean, if you guessed really this out of the blue, I would be worried for your mental health. So in real life, we want to find a method. We don't care about this c plus 1 minus cn. This shows that solution is quadratic. And that's all what we care. So in real life, we want to find recipes. If we know the recurrence, how can we estimate the asymptotic growth rate? Is it linear, quadratic, n log n, right? But the upshot here is that our divide and conquer was useless because the solution is still quadratic. Just because these 4 somehow canceled out these 2. Now the trick is, do we really need 4 multiplications? Let's go back and look at the problem. Here, you see, here we need only 3 numbers. We need A1, B1. We need A0, B0, but we don't need these 2 products. We only need their sum. Okay? And this is where this clever kid, Karatsuba, came with this wonderful solution. So what he did is he again split this into 2 halves, okay, and got the very same formula. But then he realized that in order to get this midterm, only 1 multiplication is sufficient. Namely, you simply sum A1 plus A0. That's doable in linear time. You sum up B1 by B0. So you simply add least significant part to more significant part. And then you multiply these. So that's 1 single multiplication of this sum times that sum. If you now actually expand this, you see that from this product, if you subtract these 2 terms which you have, you get precisely what you need. Okay? So the trick is that you can do it with 3 multiplications only. And here is the, oops, where is it? Don't be scared with this. Okay, so here is the algorithm. Again, take more significant part, less significant part, more significant part, less significant part. Add more significant and less significant part of the first number. Do the same for the second. Then multiply A0 and B0, A1 and B1. Store this product. How many multiplications have we done? We did 1 multiplication for A0, B0, another one here for A1, B1, another one when we multiplied U and V, and lo and behold, the rest is just subtraction and shifting, so our recurrence now looks like this. So we dropped this 4 that was here, it dropped to 3. And lo and behold, this will decrease the complexity of the solution. How do we now estimate the complexity of the solution? Now, the reason why I want to show you an ugly calculation is so that you then understand why we need something called the master theorem, which will enable us in a great deal of cases from the shape of the recurrence to apply 3 recipes that give us the asymptotic growth rate of the solution without any calculation. So the calculation that I'm going to show you will be completely replaced by a recipe, but also this calculation that is very easy to follow is essentially how you prove the master theorem. Okay? So let's see. If this is true, if this recurrence is true, I can also replace n by n over 2. And we obtain that t of n over 2 is equal to 3t, and this becomes t of n over 2 squared plus c times n over 2. Now I can replace again n over 2 by n over 2, sorry, n by n over 2, and I get t of n over 2 squared is equal 3 times n over 2 cubed plus c times n over 2. And I can keep doing that. So now I start again with my recurrence, but then I replace this term by whatever this formula tells me. So it looks messy, but it's trivial what's happening. I'm simply unwinding the recurrence, right? Substituting each t of n over 2 to the k by something t of n over 2 to the k plus 1. So if I do that, this is what I get. Now I can replace t of n over 2 squared by this, and I keep doing that, and lo and behold, what you end up after many steps is this. You can just see it, and you can see the pattern. You see here is 3/2 and increasing powers multiplied by n, and here the leading term in front of t keeps increasing as powers of 3. So if I do it, how far can I go? Each time I halve the size. How many times can I halve a number? Log n many times. So here I'll have 3 to the log 2 of n, right? And here I'll have the sum all the way to, you see it goes to 1 degree smaller. Here is 4 and here is 3. So it will be 3/2 on this power. And again, we use the same kind of sloppiness. These floors and ceilings are just a nuisance, and we simply ignore them. So this is just a geometric progression. This is what you get when you sum it. And lo and behold, you end up with this expression. Now we use the following trick, which you have to review from the little booklet I told you. Namely, logarithms have a very nice feature that a to the log b of n is equal to the expression when the input to the logarithm changes place with the basis of exponentiation. So this is the same as n to the log b of a. How do we prove this? Well, just take log of both sides, and then the exponent can get outside, and lo and behold, you get identity. So this is what I get, and when I multiply here, this simplifies further to this. So I have n to the log 2 of 3, n to the log 2 of 3, and then subtract something linear. So linear grows slower than n to the log 2 of 3, which is 1.58 and something. So we conclude the whole operation, the whole recursion takes n to the 1.58, less than n to the 1.59 many steps. And if you are multiplying really large numbers, this is much better than n squared. When do we multiply really large numbers? Encryption, exactly. So in fact, encryption doesn't do multiplication in the standard way. It uses one of these tricks. Now, the fastest way to date, well, at least when I was kind of following this a little bit, maybe 10, 15 years ago, when you were still in diapers, the fastest way was n times log n times log n. And it is due to Knut. So we don't know whether you can do it in n log n straight. You can almost do it, but not quite. We will see this later. Okay, so in the little notebook that I put on the website, please read about asymptotic notation and properties of the logarithm. And I will also assume that you know very basic algorithms like sorting. Why do we have so many sorting algorithms? For different problems. How can sorting problems be different? Exactly. So if statistics of your inputs, depending on the features of your input, you will choose accordingly the sorting algorithm. But I assume you know what quicksort is, what radic sort is. If not, look up in the Corman's book, which I also hear is available at dodgy Russian and Chinese websites, but I didn't tell you that. So I expect you to know also hashing, that hashing is, right, it's constant expected time, but linear worst case time. That binary search trees work in n log n time, no matter what. And these simple facts, so please, this is all in this little booklet plus a few interesting puzzles. Okay, now the question is, can we multiply large integers faster than n to the log 2 of 3? What do you think? Can we? How would you? So what did make a difference? It made a difference to split two numbers, the two numbers into two halves. We can split it into 3 halves. Well, not quite 3 halves, into 3 thirds, right? You can then split it into 4 parts. And do we get faster algorithms? And the answer is theoretically yes, but practically no. And this is our goal. You see, the problem with asymptotic notation like O of n squared and O of n, from practical point of view, what is the danger? When can these become totally useless?
You could have enormous constant factors.
Exactly. Beautiful. So the problem is, when you do the asymptotic notation, asymptotic estimate, you have to have some sense how big are the constants. And that will be precisely the problem with this algorithm. If we try splitting in more and more pieces, it does asymptotically run faster, but the size of the constants will become humongous very quickly. And this will tell us, then we will locate what is the offending term, where the size of constants explodes, why, and it will tell us what to replace it with to get an actually really even faster algorithm, one that runs in time n log n log log n. But that is our plan. So first we want to investigate this because it's an interesting divide and conquer. It's interesting application of the master theorem, and it also gives you reasons why you have to be cautious. Asymptotic notation is useless unless you can vaguely estimate the size of the constants. That's first thing. Second thing is, can we avoid messy computations like this? And the answer is yes. And this is why we are going to do the master theorem, because it will allow us to quickly deduce the asymptotic growth rate without doing any calculation. Okay. Now, in good old times, I also did some puzzles in class, and so that was the end of it, but you are unlucky. Namely, I have more slides for you. Okay, so the problem is indeed that you see, pretty soon all the classes, we will be on a trimester, so you have to get used. You know, we have in Serbia this dish called stuffed peppers. You take a pepper, you cut the top off, and then you push rice and meat as much as you can fit in. This is how we are going to teach you on a trimester basis. Oh man, how do I, was it F11, I think it says. Okay, so. Just a few things. Okay, so this is a little review. This was in 2005. Were you born in 2005? Probably. So please read the little booklet to refresh the basic stuff. And now we are going to talk about a little bit about recurrences. And if you behave well, I'll let you go a little bit earlier. Okay, let me see how I do that. That was not what I had in mind. Okay. So, how do I make it full screen? Probably this. Okay, so the topic is recurrences. And let us just very briefly review the asymptotic notation. F is equal capital O of G is an abbreviation for this. There exists a positive constant C, right? So that f of n is eventually smaller than C times G of n. What does it mean, eventually smaller? It means for sufficiently large n, it will always be true, okay? So here we are assuming what are the functions f and g. F will typically be the runtime of your algorithm. So it's obviously a positive and an integer valued function. And it's non-decreasing, right? You can assume that it's non-decreasing. And what does this notation say? This notation says, oh man, how was it that I managed to do it with, so that, how, oh gosh. Excuse me, the cameraman. Hello? What did you do so that I can go slide by slide? You did something.
No, you should just be able to press it. It's just press it like the exit. Show the slides on the web.
Sorry? Where is the presentation? Okay, anyone knows how, please help me. Look, when I was studying, when I was your age, we had punch cards. What do you expect me to be able to navigate to this sophisticated technology? Can we just see?
You recently opened the slides on the web browser. See the web browser?
Here is web browser.
Yeah, just.
But I want it when I press that it. Oh, good, excellent, thank you. Okay, you have extra credit. Please behave, otherwise I'll bring my wife next time. Okay, so big O notation. F of n equals O of G of n is an abbreviation of this silly kind of it says the following. I can blow up G a little bit. I can multiply it by a constant C so that it eventually becomes bigger than f of n. But the meaning is, of course, that f of n does not grow faster, essentially faster than g of n. So why would we have such a definition? Why not simply say f of n should be smaller or equal than g of n? Why? So obviously, we want to discount the effects of multiplying functions by a constant. And it doesn't have to be true for all n, but for sufficiently large n. If f is a runtime of an algorithm, why do we want to make it insensitive? Why do we want to make runtime of 3n squared be exactly the same as runtime of 10n squared? Why would you do that? Yes?
Some computers might run faster than others.
Well, not in terms of clock, but what might they have? So, instructions, they might have different instructions. So, when you need to run a new program, you simply download a new program. You don't need a new computer. Why is that so? How do we call such machines that it's enough to change the program and they can do anything possible? Well, general purpose, what makes them? How do we exactly say, why is it the case that any computable thing can be executed on any computer? It is because machines are Turing complete. What does it mean, Turing complete? Anything computable is executable on this machine, right? But computers do differ because they can have different instruction sets. So some computers, some processors like Intel, right, have gigantic instruction set. Some, like these RISC architectures, have a much smaller instruction set. So if you need a more complex operation, you need to emulate it with several simpler instructions. So, and we want complexity of algorithms not to depend on the features of the platform on which they will run. And with this notation, say all of instructions of, say, an Intel processor can be accomplished with at most 100 operations of a restricted instruction set. Well, then, of course, the runtime will become smaller or equal than 100 times the runtime of the Intel set, on the Intel machine. So for that reason, we want to make our complexity measuring system independent on the computational platform, on hardware platform. And lo and behold, this takes care of different instruction sets. And why eventually? Well, depending again on operating system and architecture, maybe there is some initialization procedure that might take different amount of time. So this is taken care by this eventually. But you now understand why we allow. So if G of n is execution time on an Intel processor, and f of n is an execution time on a RISC machine, and every operation of Intel machine can be, say, accomplished with at most 100 steps of the RISC machine, then if I put here 100, I will get that f of n is smaller or equal than g of n, right? So this is why we do it this way. Okay, that's big O notation. Big omega notation is just flipping this around. If f of n is O of g of n, which means that f of n does not run, that f of n is not substantially larger than g of n, then in the opposite direction, gee, what happened now? Now it won't do the trick that, here it is. Okay, omega notation says precisely the opposite, right? That f of n is capital omega of g of n if and only if f of n is eventually bigger than some multiple of g of n. So this is just f of n is omega of g of n, just in case g of n is O of f of n. And then we have theta, which is when both are true, both n is smaller, n is O of f of n is O of g of n, and vice versa. G of n is O of f of n. Yes?
Why do we need omega? Do we only need theta, or is there any practical use?
That's because it is customary in computer science literature to use it, but you are absolutely right. We could just use O and theta, but we define it here because in the books you will find it. And moreover, there is actually this big O is capital Omicron. And you have also small Omicron and small omega, but they are just rehashing of the very same concept. It's enough to understand what f of n equals capital Omicron of g of n means. Okay, so now we figure out that. And let us see why do I have merge sort here? We know that it satisfies this recurrence, and then, okay. So examples of recurrences. All recurrences that we will encounter come from recursive algorithms, from divide and conquer algorithms. For example, in merge sort, we have two calls of merge sort on arrays of half the size, plus merging the two arrays, which is, of course, linear in time. So the recurrence that describes the runtime of this recursive algorithm, divide and conquer algorithm, is T of n is reduced to two runs of the algorithm for half-size input plus linear overhead. Okay. In general, we will have, you will have divide and conquer algorithm that reduces a problem of size n to a many problems of size n divided by b. So A tells you how many smaller cases you get. B tells you what fraction of the original size these sub-problems are. So if we write something like this, this will come from divide and conquer algorithm, which reduced the problem of size n to a many problems of size n divided by b. And of course, a must be bigger or equal than 1, and b is b has to be larger than 1 so that this n over b drops in size, but b doesn't have to be an integer, right? Plus an overhead that we denote by f of n. And what we want is some handy recipe that if I tell you what a and b are, and if I tell you the asymptotic growth rate of f, you can look up in a recipe and tell in most of the cases what is the growth rate of the solution to that recurrence. Not exact form of the solution, but the growth rate. Okay, so, and again, we will just dispense with ceilings and floors. And you know what? And this is just to give you a visual presentation. So a case of size n is split. It's reduced to a many cases, each of size n over b. And we want a quick kind of way of estimating how many steps in total are hidden here. And because you were good boys and girls, I'll let you go now. It's enough for the day. See you tomorrow.